Sorry, starting midway through here. So we're looking at question 9 from lesson 6. I forgot to hit record at the beginning for those of you who follow me on YouTube. Sorry. So here's my picture, and this is mg perpendicular and mg parallel. Definitely a normal force. Hopefully I'm a little more with it today than I was last class. Good gosh, that was horrible. I was tired. I just hit the wall. And, oh, which way is this mass moving? So which way is friction acting? Now, some people are like, how could it be going up there? Someone off screen gave it a huge push. We just didn't see the push part, but it's sliding up the hill. So friction is going to be going that way. Who's winning? Who's winning? Friction. Who's losing? Oh, who else is winning? Okay, so my equation here is going to be, can I do mg parallel first because we're kind of used to seeing that first? So I'm going to go mg parallel. They're both winners, so it's going to be plus friction equals ma. mg parallel, two lines is sine, plus friction is mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Mg, did you say perpendicular? Of course you did, right? I would normally not do it this fast, but I'm trying to get this all on one line, on one screen. So Josh, are you okay with that? All right. And I guess what they want me to get by itself is this thing. There's the mu. What's mu? I don't know. What's mu with u? Because it said find the coefficient of friction. Well, can we agree I could minus this to that side? In other words, I think the same equation is this. Is that okay? And I think we can say because it's times divide. There's the equation, I guess, for something sliding up a hill if you want to know what your coefficient of friction is. You okay with that so far? Now I check. Did they give me the mass? Yep. Did they? Oh. Did they give me the acceleration? You know what? Even though this question is saying, what's mu? I don't know what's mu with you. Even though this question is saying, find the coefficient of friction, you know what's really asking me to find? Acceleration. Okay. Well, I can't find acceleration using forces because, oh, wait a minute. Last unit, we also found acceleration by using my DFIC approach where we said list our data. Oh, I know V final stops is 0. It does say that V initial is 4, and they gave me a distance. Did you do this part, Josh?
I solved it.
Oh, you solved it?
Yeah.
Oh, you asked me to do number 9, didn't you?
I did.
Okay, so you figured it out now?
Yeah.
I'll keep going because I see a few people with glazed looks on their faces. I think I'd use this one. A equals VF squared minus VI squared all over 2D. Now, the only tricky part here, I think, oh no, you will get a negative answer. Good. I was going to say you're slowing down. A should be negative. I don't know if, because I've let this way be positive, I don't know if I'd put the negative. In fact, I don't think I'd put the negative in there. I'd make it positive there. Mr. Dewick, is that fair game? Barely if I wanted to put a real nasty written question. Each subpart of that is fair game. I would have no problem if I gave you the acceleration saying find mu. I would have no problem if I gave you mu saying find the acceleration. Or to be honest, the question that I would probably do, I would give you mu and I would say find the distance that it slides. In other words, get A and then walk over here. Or find what V final, or what was V initial. If it went 4.06 meters, how fast was it moving at the beginning, or something like that. Is that all right? I think that'll get you there. I hope. Any other questions from lesson 6? So how about any questions from lesson 7, advanced inclines, which I know I didn't quite finish. We are going to finish. Did I assign questions from lesson 7 at all? Did I assign questions from lesson 7? I did already. Okay. Well, you know what? Let me pause the video for a second. So, continuing on from lesson 7. Basically, if I did my job right, then ideally, Manny, there was not a single new thing in the lesson. It was, I didn't think of doing that, but sure. So we said, for example, if I wanted to make the question a little tougher, I could have a rope and add a tension, which would add tension. Oh, okay. We said, oh, I could have an Atwood machine on a hill. We talked about how you could figure out ahead of time who was winning. Or we also said, Nick, if you figure it out wrong or guess wrong, you would notice you'd get a negative acceleration, and it wasn't that hard to fix. That was the whole point of that rant. We said pause here. This was we were going to be finding a missing mass. And that I do like. That is physics 12. So where it says pause here, we had left off, we had found tension. Yes? Okay, let's find a mass. Put your pencils down and look up. One way to do this, since we know that mass 2 is sliding down, we could write an equation for the entire, both masses. We could do our winner minus loser. Don't write this down. We could go M2G parallel winner minus friction force 2 minus tension plus tension minus M, don't write this down, 1G and then we would say, don't write this down, friction is what times what? I don't know the normal force. Oh, but look. I know another force the same size as the normal force, M2G perpendicular. The tensions cancel. Now, why would this work? Did they tell me the acceleration in the question? I think they did, yes? Do you know mass 1? Do you know G? Do you know mass 1? Do you know G? I'd have to, of course it is. Do you know mu? Yeah, they told you that. Do you know G parallel, that sign? The only thing you don't know is M2. You could get rid of the brackets. You could go like this. And then, how many M2s do you see? Is there more than one M2? Get them all to the same side. Is there a nice grade 9 mathematical operation? In other words, you can get M2, missing mass, from the big Uber equation. I find it easier to find tension and then go look at one mass because it's less ugly. It's about the same amount of work. So I said, don't write this down. Hopefully you didn't. Instead, I'm going to write an equation just for mass 2. So just looking at mass 2, who's winning? I think, right? Who's losing? I think we have minus tension and minus friction force 2. You guys have the free body diagram in front of you, right? That makes sense? That's going to be M2A. It's not that doing it all at once is wrong. I've just learned kids make fewer mistakes with this equation. Does tension cancel this time? No. Friction. Friction is what times what? So this is going to be M2G parallel. There's going to be a minus tension. There's also going to be a minus mu. Oh, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one? And now you got to go look at your diagram. I've scrolled down on purpose. Which force is the same size as normal force number 2? Which M? Okay, M2G perpendicular. And that's going to equal M2A. By the way, G parallel, 2 lines. Sine, minus tension minus mu M2G perpendicular. Of course it is. All right. What are we trying to find here? M2. Right? We found tension already. M2. How many M2s do you see? Let's get them to the same side. I'm going to go plus this guy over and minus that guy over. Tension's going to drop down. Oh, well, negative tension is going to drop down like a domino. Okay. And I'm going to get M2A plus mu M2G cos minus M2G sine. How many M2s are there in my equation right now? 3. How many would I prefer? Would it be cool if there was a grade 9 mathematical operation that I could pull out of my back pocket and turn this from 3 M2s into 1 M2? There is, you say? Which one? We did this the other day. Yeah. Factor, GCF. Greatest in English we say GCF, factor, whatever it is in the other languages. But yeah, there's a common term of mass 2 and everything on the right. So I can go negative T equals M2. And then, Dustin, I guess it's going to be A plus mu G cos minus G sine. Is that okay, Dustin? And how would I get the M2 by itself, my friend? Okay. Do you guys want to, I can keep going, or do you think you have the hang of it right now? Keep going? Okay, so we'll actually solve it. If I hear you correctly then, Dustin, you're saying M2, you're saying the negative T just drops down. I'm going to divide it by that whole mess. Sure. Negative, I can do that. Tension was 90 something, 95.2. All over. A. Please tell me they told me it. 2.1. Plus, what's mu? I don't know. What's mu? What did I say mu was? 0.12. G. Hey, I know that one. Cos 28. Plus, Mr. Dewick, minus, copy the equation down right. 9.8 sine 28. Hey, is there more than one number on the top? Oh, I don't need brackets on the top. Is there more than one number on the bottom? I better put the bottom in brackets. Did I actually? I don't think I actually assigned questions from lesson. Or no, I think I did assign questions from lesson 7. I can't remember. That was a whole 2 days ago. I was out of it. Hopefully, I've told you it's worth practicing on your calculator for these more complicated expressions. I'm getting the mass. First of all, I was a little worried with that negative on the top because I know masses are supposed to be positive. Did I get a positive mass? At least it reassures me maybe my physics is right because the answer is kind of what I hoped. Also, looking at this diagram, I think mass 2 does have to be bigger than mass 1 because it's winning and it's on a slanty hill, so it's not pulling straight down. Did I get an answer that's bigger than mass 1? I think 65.1. Anybody else get that? I should have asked first. Yeah? Okay. Whew. Did I rattle off which questions you should try for this last class or not? I didn't? Okay. Give you the same. Well, you know what? I'll just remember. Number 1 is fine. Now, number 1, they gave you, if you look really close, mu k and mu static, mu kinetic and mu static. But you notice it's the same number for both. This is me saying, just pretend there's one type of friction. Mu is 0.1. Why didn't you put the symbol? Because it was tough to find when I was typing. 2 is good. 3, and I'm going to do this. Well, you know what? It's frictionless. If 3 had friction, I would call that too hard and overkill, because you're finding a mass. Is there friction? Then you know what? This won't be as bad. 4 is good. Skip 5. 6 is kind of cool, but skip it. That's finding theta, which means somewhere along the way you would end up going shift sine or shift cos, but eh. I like number 7, I like number 7, I like number 7. Number 7 is a nice question. I like number 8, I like number 8. Number 8 is a nice question. Number 9 is tempting. It's a water skier, but I'll pass. In fact, you know what? I'm just going to assign those ones for now, because I'm going to be giving you more stuff. Sorry. Let's see if we can finish off the unit, or at least come close enough so that on Tuesday I teach for about 10 minutes and you have the rest of class to work on take-home quizzes and practice. Lesson 8. Hey, let's finish off the unit. What's that you say, Clay? Oh, you love learning physics? Yeah, this is great. Wide awake? How can you be tired now? Absolutely. First type of question I call the lawnmower problem. I love the lawnmower problem. I love the lawnmower problem. I love lawnmower problem. Will you marry me? What does that mean? You can absolutely guarantee positively something. I'll let you figure out what I'm getting at, okay? What do I mean by the lawnmower problem? I'm assuming most of you have either pushed or seen a lawnmower. It's where the ground is flat, but the force is at an angle, as opposed to the ramps where we had gravity at an angle. You know what? It means the normal force ain't no mg. There's going to be some other vertical component. And there's two possibilities. Either you're pushing down, like in this picture, along the handle, along the force. Normal force is going to get bigger because when you push down, the ground has to push up harder. Or you might see in the homework, maybe you're lifting up, in which case the normal force is going to get smaller. By the way, if the normal force changes, what other force does that affect? Which other force has the normal force in its equation? Friction. Okay? So what's the definition of a lawnmower problem? Where we have vertical force components other than normal force and mg. The ground is flat, the forces are not. So in a problem like this, the normal force won't be mg, or if I'm really mean and give you a ramp with forces at different angles, the normal force won't be look, mg perpendicular, of course it is. Will I give you one like that in the homework? Yes. On a test, no. But certainly I like example 1, I like example 1, I like example 1. Example 1 is a nice question. It says find the normal force, find the friction, and find the acceleration. Clay, let's be clever. Let's call this part A, this part B, and this part C. I keep forgetting to do that. Hopefully now when I say, any suggestions on how we should start? All of you have an obvious answer. How are we going to start this question?
Everybody diagram.
Yeah, and did they give me a picture, Clay?
Yep.
Then I'll just label their picture itself, okay? What are the forces acting on this? Get the obvious one.
Gravity.
Gravity. What else? Now, normally, typically, we've said, is it sinking into the ground? Is it flying? And we've done the normal force, but I'm telling you, the normal force is going to be weird here. So let's save it for last. Okay? What else? Is there friction? Which way do you think this lawnmower is going to accelerate? So which way would friction be acting? What else? Well, you know what? the applied force, which is this 200 newtons downwards at an angle of 20 degrees with the horizontal. I'm going to say this again. Listen closely for a key word. This 200 newtons downwards at an angle of 20 degrees. Did I say angle? What might that make you think of? So I'm going to break this up into pushing down and pushing sideways. Okay. I'm not going to call them parallel and perpendicular, and you'll see why in a second. Are we on flat level ground? What letter have we typically used for vertical, and what letter have we typically used for horizontal? You know what? We've gone to graphing, haven't we? I'm going to call this Fy and Fx. So here's my question. How big is the normal force? Are we sinking into the ground like quicksand? Are we flying into the air like Superman? So everything down has to cancel out everything up, or everything up has to cancel out everything down. So don't write this down. Why would that be wrong? Manny, loud and proud. The normal force is going to be bigger. In fact, it's going to be this long plus this long. If I eyeball it, probably about, you know what, even a bit longer than that. This would make, for Physics 12, a great free body diagram to ask you to draw. And if I did, I would absolutely be looking for a normal force that was bigger than mg. Or what if instead of pushing down, what if we were tugging up at an angle? What can you tell me about the normal force then? It'd be shorter than mg, I can tell you that. This is why pushing on something and pushing down on it while you're trying to slide it makes it tougher to slide, because you're making the normal force bigger, which makes friction bigger. This is why lifting up as you try and slide something makes it easier to slide. You haven't changed mu. You haven't changed mg. Which force have you changed? And hopefully now we're coming full circle, and I'm really convincing you this is why back when we defined friction, we said friction is not mu mg. It's mu times how hard the ground has to push back up, which we call the normal force. All right. What does part A want me to find? I'm going to argue, I think the normal force here equals gravity and Fy. It can't, what goes down cancels out everything that goes up. That's what you were saying, yes? Fy, you know what? Let's get tricky with it. Here's my angle. The 200 is the hypotenuse, I think, yes? Fy, opposite adjacent or hypotenuse. Which trig function is Fy? Now, by the way, there's a reason I labeled it this way. Don't write this down. If you had labeled this perpendicular, which it is to the ground, unfortunately this time perpendicular is not, of course it is, it's sine, and I don't want to confuse you. So I use parallel and perpendicular on ramps. I go back to y and x for vertical ground. Let's just convince ourselves that Fy does work. I think it would be the sine of the angle. Someone's phone just went off there, taking a picture there, mister? Kohei, we'll be looking for some Timbits later. I don't know what it is about the basketball team, but it seems like they're having a little difficulty with this whole phone thing. Fy over, oh, you know what? Instead of putting the number, I'll just put F applied. How would I get Fy by itself? How would I get the Fy by itself? Times by F applied? Okay, so I can say Fy is the applied sine. So we can go like this. Normal force equals mg plus F applied sine theta. There's my generic. We'll plug in numbers in a second. Now, if we were lifting up, this would be a different equation. What would the equation be? I think maybe mg minus, but honestly, I'd have to draw the free body diagram and derive it. Why would I memorize extra things when I can just derive it in 1 second with a lovely picture? So we're going to get this. The normal force equals 50 times 9.8 plus 200 sine 20. I get a normal force of 558.4. Oh, I'll call it 558. Is that right? Yeah. I'll go 558 to 3 sig figs, but I'll keep this number on my calculator. Units, normal force. Oh, did you say force? Newtons. What did B want me to find? Oh, friction is mu times the normal force. I don't know the normal. Oh, wait a minute. Ha! I do know the normal force. Who knew? What's mu? 0.1. What's the normal force? 558.4. Don't reach for your calculator. Isn't timesing by 0.1 just the same as dividing by 10? I mean, you can try this, but isn't the answer going to be 55.8 newtons, I hope? I see someone looking a little dazed. Right, 55.84, blah, 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 blah. Now, I'll be honest, the odds are pretty good if I did give you this question. The odds are pretty good if you see this question in the future. I won't ask part A or part B. I'll jump straight to part C, and I'll expect you to clue in. Normal force is different. Friction force is different. Be careful. Because what's part C want me to find? Acceleration. Which way is this thing accelerating? If it's accelerating at all, it's accelerating to the right. So who's winning? Acceleration is not a force. F applied is slanty. I will never use a slanty. Ah, do you see it now? Who's winning? Fx. Who's losing? Here's my equation. And that's what makes that second, first of all, the normal force has changed. The second most common mistake that I see, kids want to use that 200. You know what? If I was a good teacher, I would have gone on a rant about how we never use a slanty in our equations, and that 200 is a slanty. Fx. You know what would be kind of cool? If Fy was sine, what would be kind of cool for Fx? Let's find out. Oh, you know what? It is adjacent over hypotenuse. Let's just confirm it to really convince ourselves. I think I would say cosine of 20 equals Fx over the applied. How would you get the applied by itself times the, sorry, the Fx by itself times the applied over? So I think we can say F applied cos. I think we can say of cos it is theta minus 55.8 equals m. Wait a minute. What are they asking me to find? You know what? Look up. I'm going to go. I figured that one we can do kind of casually, dividing by an m. We've been doing that for a while. Now I think we're plug and chug. The acceleration is going to be applied force is 200. Cosine of, what was the angle, 20? Minus, now I'm going to write 55.8, but I think I still have this stored on my calculator with more decimals. All over, what was the mass? 50, I think, yes? Now, by the way, what if I get a negative answer here? It means I'm pushing down so hard that friction is so big that I'm not going anywhere. Will I get a negative answer? I don't know. This is well beyond me being able to do this in my head. Minus answer button. Oh, we are accelerating. 2.64, is that right? If you carry all the digits, I'd take probably 2.63, 2.65 if you round it off, but try not to. 2.64 what? Meters per second squared. So there's an example of a lawnmower question. Here, instead of pushing down, now we're lifting up. Maybe instead of a lawnmower handle, it's a rope and you slung it over your shoulder and your shoulder is higher than the box. That happens fairly often if you're trying to pull something with a rope. You want to put your back into it. Do you guys want to try this on your own, or do you want to do this together? Or I can do it up here without talking. You can try this and look up along the way, or what? Sorry? You want to do it we can do it together if you want, but I've been yakking quite a bit. You know what? Let's first of all, how would we start? All right, what are the forces acting on this 7? Get the obvious one. By the way, are we lifting up, or are we at an angle, or are we pushing down at an angle? Lifting up. Is my normal force going to be bigger than mg, smaller than mg, or the same size as mg if I'm lifting up at an angle? Spencer. So you know what? This time I will draw, because I noticed that, I'll draw in the normal force, and I'll really exaggerate it. I'll make it smaller so it's clear to me that don't do the look, right? What else? We have an applied force. Is there friction? I'm going to do one more thing. Is there an angle? Why, oh, good. Hopefully that's becoming a habit now. Components. There's going to be Fx and Fy. Can you see what the vertical force equation is going to be? What equals what vertically? Which forces? Yeah. Yeah. It will be if you're lifting up, I think. Give me 1 second, and I'm going to answer your question, but I'm going to answer it mathematically. I would argue here, vertically, I have this. Is that right? Is this sinking into the ground like quicksand? No. Is it flying into you like Superman? No. Everything down equals everything up. If I get the Fn by itself, yes? Yeah, you can write. Yeah, write this down. I don't think I said don't write this down. Josh, is that okay? There's an arrow. It's lifting up, and if you're lifting up, because if you're lifting up, I guarantee you'll get this line right here, and you'll get this line right here. Oh, normally the normal force is mg, but we're subtracting something from it. It must be smaller, because you're subtracting from mg. Compare that with when we were pushing down. Then we ended up with normal force equaling those two added together. Again, normally normal force is mg. Oh, you're adding to it. It's going to be bigger. Oh, and therefore friction will be bigger. Therefore friction will be smaller. It'll be easier to slide. Is that okay? Think? In other words, if you're lifting up, normal force must be smaller. Okay, we'll come back to it if you want. We can ask me later. Who's winning? Don't say the applied force, because we never use a slanty. Who's losing? I'm going to do the rest on my own. Try working ahead. Try doing this. If you get stuck, look up. I'll kind of talk to myself a little bit. Adjacent hypotenuse fx. Of course it is. Now let's change colors, Mr. Duke. I don't know the normal force. Oh, but ooh. I can't go. Oh, wait a minute. There's the normal force. Sorry, I wrote F applied. Fx is going to be F applied. Good gosh, Mr. Duke, you made a dumb mistake. It's going to be F applied. I said of course it is, and I forgot to write the cos. That was dumb. Minus mu. I think I'm going to have to use brackets here because this whole thing is the normal force. That equals MA. The applied force times cos theta minus mu mg fy. So, the applied force sine theta equals, you know what, I'm going to divide by m on this line right here because I can't get the a by itself. Clay, do I know the applied force? Did they tell me?
No. Yes.
What?
18.
Okay. They told me theta, 21. Did they tell me what's mu?
Yeah.
What?
0.23.
Okay. I know m. I know g. I know the applied force. I know theta. And I'm, oh, you know what? This is plug and chug. Complicated, yes, yes. But it is now plug and chug. I'm going to be really, really careful. So, A equals, what was the applied force? 18 newtons. Cosine of 21 minus, what's mu? I don't know, what's mu with you? 0.23. What was the mass? 7 times 9.8 minus 18 sine 21. All divided by 7. I think that's right. Oh, and if I get a negative answer, friction is too big, this thing's not moving at all. But I think because we're lifting up and thereby making the normal force smaller, I think friction is going to be smaller. I think we're going to be okay. Let's see if I can do this in one fell swoop. More than one number on the top. 18 cos 21 minus 0.23, and now I have to have a bracket. 7 times 9.8, take away 18 sine 21, close off the sine, close off that bracket, close off the top. I think it's 3 brackets. Let me double check. Open the top, close off the top. Open the bracket, close off the bracket. Yeah, I think I'm right. I think I'm good. By the way, I don't know if I would do this all in one fell swoop. I might be tempted, Nick, to just crunch that, store it as an answer on my calculator using my answer button, because then it would be 18 cos 21 minus 0.23 answer button divided by 7, which might be a better way to go. But I was curious to see if I could do this the whole way. Anybody else get 0.3585, 0.359? Anyone else? Yeah? Got 2, 3, 4. Okay. So I think I'm going to go 0.3. Oh, change colors, Mr. Duke. meters per second squared. By the way, if it didn't move at all, what would the acceleration be? Meant to be really obvious and a trick question at the same time. 0. You know what? Another, instead of me giving you the acceleration, I could say, hey, what if it doesn't move? What's mu? Okay, I'd end up having to get this thing by itself. I could do it. Be ugly, but I could do it. Turn the page. Clay is static equilibrium. The static equilibrium problem. The definition of something that's in static equilibrium is an object that is at rest. Actually, there's a better definition. The total force is 0. It's not accelerating. Which really means if the total force is 0, what's the acceleration? 0. All the forces are balanced. This is true for both the horizontal and the vertical forces. It says find the tension in both cables. So it looks like we have a cable like this and a cable like this, and this is like a sine or something like that. Any suggestions? Label, okay. What are the forces acting? Now, I'm going to give you some advice. Look up. You'll find it way easier if you list the forces that are acting right there. Imagine that the mass is sitting right there. What are the forces acting right there? Get the obvious one. What else? Tension? In fact, how many ropes are there, Clay? How many tensions are there? How about I call this tension 1, which I think is pulling upwards that way, and tension 2, which is pulling straight sideways. Now, if I was also drawing the forces on the wall, there would be, don't write this down, a Newton's third law tension there and a Newton's third law forces come in pairs tension there. But I'm not drawing the forces on the wall here. You know what? That's it. Those 3 forces cancel each other out. I'm going to say the same thing. I'm just going to phrase it differently. Those 3 forces add to 0. These kind of look like, what do you call, something with the letter V and rhymes with vectors. Oh, vectors. I'd like to add these together. Any suggestions on how I might want to add these together? Tip to tail. Okay. Now, I am not going to give you, you can make a little note. I'm planting a seed. This will be on a test at about 5 units from now, but I always kind of plant the seed now. How many different forces are there in this question? 3. I'm going to draw a triangle, okay? This is your first real introduction to a 3-force vector diagram, and here's my advice. I always draw the easiest one first. Of those 3 forces, what's the easiest or obvious one? There's a reason I taught you that. I'm going to draw this first. Yoink, there's gravity. I draw the toughest force next, the slanty one. I'm going to draw it tip to tail. See if you can tell me, Nick, you going to make it? You're looking a little dozy there. See if you can tell me when to stop. There? 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 Oh. Why do I want to stop right there? Look at the third force. What must the third force look like? And do you notice that when I follow this, I end up back where I started from? If that was a displacement, what's my displacement? 0. It's not displacements, it's forces. What's my net force? 0. There's a picture of a net force of 0 in 2 dimensions. Now, why is that nice? Are you telling me, Mr. Duke, Pythagoras and little trig? Yeah. Let's fill in what we can. This is mg. This is tension 2. This is tension 1. I notice that next to tension 1 and a vertical line is 35 degrees. I think next to tension 1 and a vertical line is, I think that's the 35 degree. Do we know the mass? Do we know the mass? Yeah. So then do we know mg? We're going to use that. Can you first of all, mg, opposite, adjacent, or hypotenuse? Tension 2, opposite or hypotenuse? Tension 1. Which trig function could I use to find tension 1? Cos. Well, no, unfortunately now my stupid rules break down, which is also why I'm not doing this right now. You have to derive each one individually. It is cosine of 35 equals adjacent over hypotenuse. Ugh. I don't like where tension 1 is. Where is tension 1? On the bottom of a fraction? Wait a minute, isn't that the same as stuff moves diagonally? I can move it to the top? In fact, this can move to there while that moves down to there. This is 1 fraction equals 1 fraction. We're coming full circle. So if I hear you, is this right? Tension 1 equals mg over cos? 35? I'll crunch that in a second. Hey, what kind of a trig function could I use to find tension 2? I don't know if I would use sine. I could, but if I use sine, I'm also using tension 1. If I get tension 1 wrong, I'm also going to get tension 2 wrong. What would be if I was a good test writer, what would be probably a smarter one to use? Tan. Yeah. I haven't used tan for a while. Opposite over adjacent. And also you'll notice this one, how would I get tension 2 by itself? Times by mg. And in other words, you get very different looking equations too. Here, tension 2 ends up being mg times tan 35, where tension 1 ends up being mg divided by cos 35. So I wrote, for example, for if you draw the vector addition of forces, you know what we did up here? Note that if the object is at rest, you get a 0 resultant. You get a closed triangle. Now, there is another way I could have done this. Is there an angle? I could have broken this up into components. I'm going to argue here, though, components suck. They're way longer, because I was able to get this in one diagram and then 2 lines apiece. But if you want a head start just with what I've done so far, you can do some of these lawnmower questions. Number 1, if you want to get a head start. Number 2. Number 3 is overkill. It's cool, but overkill. Number 4 is overkill. Cool, but overkill. 5, cross out. In fact, I'm going to skip 6. I'm going to skip 7.
8, 9, 10, 11, 12, 13.
I'll cut you some slack.
Is that 8,
So far, I've assigned 1 and 2 and 11. Here's a lawnmower question. Basically the same one as I gave you, except I've changed the force and I've changed the friction coefficient. And then here's a bunch of lawnmowers. Number 12, 13, 14, 15, 16. But I'll give you time to work on these as well on Tuesday. Your real priority, I want to give you, I was hoping to give you 25 minutes. You're going to get 22 minutes. Take a big chunk, catch up on everything we've done so far, okay?